Welcome to my channel, Worldwise. You need to watch this if you struggle with understanding Earth's ancient history. Our Earth is very, very old. It formed about 4.5 billion years ago. For a long time, it was a hot, messy place. Volcanoes erupted constantly, asteroids crashed down, the air was not good for breathing. Then something amazing happened. Life appeared. This was not life as we know it now, just tiny, tiny things. These were the first living cells. They were very simple. These first cells were called unicellular organisms. Uni means one, so they were single-celled. They were incredibly small. You would need a powerful microscope to see them. These tiny life forms showed up around 3 billion years ago. For over 1 billion years, Earth was lifeless. Then these little specks of life began. They lived in the oceans. The land was still quite barren. These cells were tough. They were the pioneers of life. Scientists call them prokaryotes. They did not have a nucleus. These early cells were more basic. They just had their genetic material floating around inside. But they could do important things. They could eat, grow, and make copies of themselves. This was a huge step for our planet. Life had found a way to begin. These tiny organisms changed the world, all thanks to these humble, single-celled beings. For a very, very long time, life stayed simple. Those single cells ruled the Earth. They were the only game in town. Imagine, for nearly 2 billion years, nothing much changed. There were just different kinds of single cells. They floated in the oceans. They formed slimy mats. It was a world of microbes. This period is sometimes called the boring billion. But perhaps it was not so boring for the cells. They were busy evolving. They were adapting. They were setting the stage for something bigger. Then another amazing thing happened. Life took a giant leap. Some cells started to stick together. They began to cooperate. They formed larger structures. This was the beginning of multicellular life. Multi means many. So these were organisms made of many cells. This was a revolutionary idea for life. Instead of every cell for itself, they worked as a team. Different cells could do different jobs. This allowed for more complexity. It was a game changer. The first clear evidence we have of multicellular animals comes from around 600 million years ago. And what was this pioneering creature? It was something quite humble. It was a sea sponge. So we have simple cells around 3 billion years ago. Then we have sponges around 600 million years ago. That sounds like a nice, neat story. But there is a problem, a very big problem. What happened in between? There is a huge gap in the fossil record, a gap of about 1.2 billion years. Think about that. 1,200 million years. That is an enormous amount of time. It is longer than the entire history of animal life. And for much of this period, the fossil evidence is frustratingly scarce. What are we missing? We are missing the story of how simple cells became complex cells. We are missing the very first attempts at multicellularity. Those sponges did not just appear out of nowhere. There must have been earlier, simpler forms. There must have been a long, slow process of evolution. How do we know about Earth's history anyway? We read the rocks. Rocks are like Earth's diary. They record what happened over billions of years. Most of the rocks we see at the surface are sedimentary rocks. These rocks form in layers. Imagine a lake or an ocean. Sand and mud and bits of dead things settle at the bottom. Over time, more layers pile on top. The lower layers get squashed. They turn into rock. Each layer is like a page in the diary. These layers are called strata. The study of these layers is called stratigraphy. It is a very important science. Geologists can look at a cliff face. They can see the different layers stacked up. The layers at the bottom are usually the oldest. The layers at the top are the youngest. It is like reading a book from bottom to top. Each layer tells a story. It tells us what the environment was like. Fossils are a key part of this story. These fossils are preserved in the rock layers. These fossils tell us about the history of life. Section 5, Hutton's Gap and Powell's Canyon, Uncovering the Unconformity. The story of the Great Unconformity really begins with a clever Scotsman. His name was James Hutton. He was a geologist in the late 1700s. Hutton was a great observer. He looked at rocks very carefully. In a place called Sycamore Point in Scotland, he saw something astonishing. He saw old tilted layers of rock, and on top of them there were younger horizontal layers of rock. There was a clear boundary between them, a sharp line. It was a massive unconformity. Hutton realized what this meant. A lot of things had to happen. First, the older rocks formed in layers. Then these layers were tilted and lifted up. Then they were eroded away by wind and water. A huge amount of rock must have been removed. Then the land sank again. New horizontal layers formed on top. Hutton understood that this process would take an immense amount of time, millions and millions of years. This was a revolutionary idea. Most people at the time thought Earth was only a few thousand years old. Hutton saw no vestige of a beginning, no prospect of an end. Almost a century later, another explorer saw something similar. This was in a much grander setting. Section 6. When Earth froze over, the snowball Earth hypothesis. So what could cause such a massive loss of rock? How could a billion years of history be erased? One of the leading theories is quite dramatic. It is called the snowball Earth hypothesis. This idea suggests that our planet completely froze over, or at least nearly completely. Not just a little ice age, we're talking about a deep freeze. Glaciers covering almost everything, from the poles to the equator. The oceans might have been covered in thick ice. This deep freeze is thought to have happened a few times, between about 720 and 635 million years ago. This timing is interesting. It is right before the appearance of those first complex animals like sponges. And it is during that long period of missing rock records. The idea is that these global glaciations were incredibly powerful. Huge sheets of ice, miles thick, would have scraped across the continents like giant bulldozers. They would have ground down mountains. They would have eroded away vast amounts of rock. The evidence for snowball Earth is quite compelling. Section 7. A weaker shield, the magnetic field connection. The snowball Earth hypothesis is a strong contender, but it might not be the whole story, or there might be other factors involved. Another intriguing idea involves Earth's magnetic field. Our planet has a magnetic field. It is generated by the molten iron core. This field acts like a shield. It protects us from harmful solar wind. Solar wind is a stream of charged particles from the sun. Without our magnetic shield, this radiation would bombard the surface. It would also strip away our atmosphere. What if Earth's magnetic field was much weaker in the past? Or what if it disappeared for a while? Some scientists think this might have happened. The period we're interested in, that Neo-Proterozoic era, is a long time ago. Reconstructing the ancient magnetic field is tricky, but there is some evidence suggesting it might have been unusually weak. Or perhaps it was undergoing frequent reversals, or even collapsed for extended periods. Section 8. Unlocking the past, why the great unconformity matters. So we have this enormous gap in Earth's rock record, the great unconformity. It represents over 1 billion years of missing time. Right when life was supposedly making its big move from simple cells to complex animals. Why is it so important to solve this mystery? Well, for starters, it is one of the biggest puzzles in geology. Geologists are like detectives of deep time. They want to piece together the full story of our planet. A billion-year gap is a huge missing piece. Understanding the great unconformity is also crucial for understanding the history of life. Was the erosion caused by snowball Earth events? If so, how did these extreme climate changes affect early evolution? Did they create a bottleneck for life, or did they spur innovation? Perhaps the intense erosion dumped a lot of nutrients into the oceans when things thawed. This could have fueled the rise of algae, which in turn produced more oxygen, paving the way for animals. The geology and biology are deeply intertwined. Then there is the question of what exactly was lost. What kinds of rocks were eroded away? Did they contain fossils of transitional life forms? Were there bizarre early experiments in multicellularity that we will never know about? Finding even small remnants of these lost rocks would be incredible. It would be like finding a lost manuscript by Shakespeare. Scientists are always looking. They use new techniques. They re-examine old locations. They drill deep into the earth. Watch my next video now.